So we want to kind of put everything together that we've been working on this unit to talk about how we can factor any polynomial, even if it's not a quadratic type, even if it's not a sum or difference of cubes or a difference of squares, or if factoring by grouping doesn't work. And so we want to have some strategies for how to do that. So the first thing we want to talk about is the factor theorem. And the factor theorem says that for any polynomial, x minus a is a factor if and only if p of a is equal to 0, meaning that, a is one of the roots. I do want to point out this terminology right here. If you ever see IFF, it is not a typo or misspelling, at least in the math context. It means if and only if. So it means that it works both ways. If p of a is equal to 0, then x minus a is a factor, and if x minus a is a factor, then p of a has to equal 0. It works in both directions. And so that's what if and only if means. But that is the notation for that. So if you ever run into that, again, language is a big part of what we're learning this year, and that's one of the languages of math. So if we have the polynomial x cubed minus 5x squared plus 2x plus 8, we want to know, is x minus 4 a factor? So if I want to know if x minus 4 is a factor, I'm asking, will it divide it evenly, which means can it divide it with no remainder? And so in this case, because it is just a linear factor, with just x, I definitely think synthetic division is the quickest. So do a little synthetic division, and we find that the remainder is 0. Therefore, it is a factor. Well, if it is a factor, that means that we get x minus 4 times, we've already done the division. So we know what the quotient is, what times it is, and so that would actually give us x squared minus x minus 2. Well, just by having that one known factor and dividing it out, that got us down to a quadratic. Well, this we could factor again. Two numbers that multiply to equal -2 and add to equal -1 are -2 and +1. So that actually gets it to a point where we can finish factoring it. And so now we can find all three linear factors that when multiplied together gives us this polynomial. Now this question only asks, is it a factor? And so the answer to that is yes. We always want to make sure we answer the question. But I want you to be thinking about how this is useful. If we know a factor, we can divide it out and get down to a polynomial that we might actually have a method for factoring. And that will allow us to continue to factor a polynomial. But you have to have one that you can at least divide out. So a couple of terminologies. Remember solutions. So a solution is something if you have an equation and it's just one variable or two variables, but you have an equation and you're actually trying to solve for what x is equal to, that is a solution. If we don't have an equation where it's equal to like a number, but it's just in f of x form or function form, we often refer to that as roots. So roots and solutions, again, talking about the exact same numbers, the values that x is equal to. And when it isn't a function like f of x form, we also refer to those as zeros because it's where that function has an output of 0, which we also know are the x-intercepts. So again, a big deal here is remembering that solutions, roots, zeros, x-intercepts, they're all the same numbers. They're interchangeable. So if I know an x-intercept, I know a root. If I know a root, I know that I can find a factor for it because x minus that root is always going to be a factor. And if I know a factor, I can divide it out and so forth and so on. So all of these things are interchangeable because they're all using the same numbers. And it's really useful that they're all using the same numbers. So if I have a polynomial function and they give me one of the zeros, All right. If this is the function and this is one of its zeros, that means that x minus 2 must be a factor of it. And if x minus 2 is a factor of it, that means that it will divide it evenly. So if I do the synthetic division, notice that this is actually the root, 2. The factor is the one that's opposite of it. But when I do that synthetic division, I did get 0 for my remainder. It did, in fact, divide it evenly. So that means that when this factored, it was x minus 2 times x squared plus 5x plus 6. So this was factored. Well, this polynomial, this quadratic, could still be factored. Two numbers that multiply to equal 6 and add to equal 5 are 2 and 3. So it factors again. So in its completely factored form, we get x minus 2, x plus 2, and x plus 3. And so that means that the other two roots have to be negative 2 and negative 3, because we have it in its factored form. So just having the ability to know 1 or 2 zeros, x-intercepts, solutions, or factors allows us to divide out those known factors, and then whatever's left over, we then use all of our common factoring tools to try and factor it. We've also learned that sometimes you get down to a quadratic factor and it's prime. So some polynomials we can only get down to linear and quadratic factors, but we're always trying to get a polynomial down to all of its linear factors, if that's possible. So let's take a look at this one. So they have given us 1, 0, and we need to find all the other zeros. So I know 1, 0 is negative 3. So I want to acknowledge the fact that x plus 3 is one of the factors. So I'm going to do synthetic division. I'm going to divide by x plus 3. I do need to pay attention here, though. I need a placeholder. I'm missing an x squared. And if I don't put that placeholder in my synthetic division, it's going to turn out wrong. So it's going to be 1, 0, negative 7, 6. And when we do our synthetic division, I did get that 0 remainder. Remember, it has to have a 0 remainder or it's not a factor. If that number had not turned out to be 0, some kind of alarm needs to go off in my head to say, oh, that's not right, because it wouldn't be a factor. So that means this other factor is x squared minus 3x plus 2. And that, I believe I can factor. Two numbers that multiply to equal 2 and add to equal negative 3 are negative 2 and negative 1. So it factors to be x plus 3, x minus 2, and x minus 1 is the factored form. And if I'm finding the remaining zeros, the remaining solutions, I just need to set those equal to 0. So x is equal to 2 and x is equal to 1. That will give me the other two zeros. Again, remember our fundamental theorem of algebra. If the degree is 3, it has to have 3 zeros. It has to have 3 roots. So this was one of them, and these were the other two. Now, the rational root theorem is going to be what really takes us over the edge and allows us to find as many of the roots as we can when we don't have graphing technology. To be perfectly honest, if I'm looking to factor a really large polynomial and I do have graphing technology handy, whether it be Desmos or a graphing calculator, the easiest way to find the factors or things that we can go ahead and divide out is to find the x-intercepts. X-intercepts are zeros. They are roots. Therefore, they will be a factor. And so x-intercepts on a graphing technology is by far the easiest way. But we also know we're not allowed to have graphing technologies in these courses over at NC State. So we have to have another way. And obviously, there was a way to do it before there were graphing technologies. And this is how that was done. This is the rational root theorem. And the rational root theorem says that suppose a polynomial equation that has integers as its coefficients has a root p over q, where p and q are relatively prime integers. Then p must be a factor of the constant term of the polynomial, and q must be a factor of the coefficient of the highest degree term. And so that uses all of our formal vocabulary. But what it's really basically saying is that if we have qx to the n power plus ax to the n minus 1 plus blah, 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 plus hx plus p. So it's some polynomial, right? And it can have all kinds. It can be to any degree. It can have as many terms in between as you want it to have. P is the constant term, and Q is the leading coefficient. Any rational root, because when this gets factored out, it's the linear factors that give us rational roots. Any rational root is going to be made up of some factor of the constant, because remember, these last numbers here all multiply to give us that constant. So these are all factors of that number. And so any rational root is going to be a factor of this number divided by a factor of this number, because again, this first term comes from taking all of these first terms and multiplying them together. So all of these are factors of that number. And that means that every rational root is always some factor of p divided by some factor of q. Always. Because that's how factoring works. These are all factors of q, and these are all factors of p. And if I'm going to get a rational root, it's going to be because one of these is equal to 0, and it's that divided by that. So rational roots always have to be of this form. What that means is that if we have a big, long polynomial, if we take all the factors of p, and we take all the factors of q, and find all the combinations of ways to divide those two numbers, we now have a list of actual numbers that the rational root has to come from. And that may not seem terribly useful when you're sitting there looking at a list of 16 numbers, but testing 16 numbers to see if one of them gives us a 0 remainder is a lot easier than the prospect of taking every number in existence and testing it to see if it is equal to 0, which we know is not actually possible. So it does narrow your field down from infinite to 16 or 12 or 4. Sometimes they're short lists, especially when we have prime numbers there. But it helps us to find something that we can divide out of it. So let's see what we're talking about. So we want to solve this equation, and we are going to use the rational root theorem to help us. So the problem with this polynomial is that, well, it's a quadratic, so we could factor it. In fact, we know 4 times -1 is -4, and that would be two numbers that multiply to give us -4 and add to equal 3. So x plus 4, x minus 1, and when we divide by 4, that's where we end up with x plus 1 and 4x minus 1. So this one would factor. But if it was a larger degree, we would be stuck. But what I want to show you is how the rational root theorem works to help us do this. So let's say this was a larger power, and I didn't know how to factor it. I know that my rational roots have to be some factor of this number divided by some factor of this number. So I start thinking, what are the factors of -1? Well, 1's prime, so really positive and -1 are the only factors of 1. And factors of 4 would be positive or -1, positive -2, and positive -4. So when we think about all the combinations for that, we can have 1 divided by 1, which would be 1, 1 divided by 2, which would be 1/2, and 1 divided by 4, which would be 1/4. And that gives us a list of 6 actual numbers, because remember, it could be 1 or -1, 1/2 or -1/2, 1/4 or -1/4. So that's a list of 6 possibilities. I want to put a big emphasis on possibilities. The rational root theorem isn't saying that all of those are zeros of this function. What it's saying is that if that function has a rational root, that rational root has to be one of these numbers. We also know that it might not have a rational root. That's a quadratic, so it could be too imaginary or it could be too irrational. But if it has a rational root, it would have to be one of these numbers. And so then we have to start going down the list. Check 1. If we did synthetic division with 1, we did not get a remainder of 0. So that's problematic. 1 is not a rational root. And that's okay. That's the big deal here, is that not all of these numbers are actually a rational root. When we go to check -1, though, we do get 0. That makes sense. When we factored it, we had already figured out that x was going to have to be equal to -1. So that was one of them. And it also gives us the other factor, because that means if x plus 1 is a factor, 4x minus 1 is a factor. And so then we can find that the other root is also rational, and it's also on this list. So both of those rational roots ended up on our list of possibilities. Yes, these other 4 were not rational roots, but we narrowed down the list of every number known to man down to just 6 that we needed to test, which definitely makes it go a lot faster. So let's look at another one. So if I want to solve, I'm always looking to factor. So when I look at factoring by grouping here, I notice very quickly that they're not going to have a common factor. So factoring by grouping is not going to work. So then I'm like, well, I need to try and find a rational root. If I can find one rational root, then I can divide it out, and it should leave me with a quadratic, because this is cubic. So if I can find one rational root and divide it out, I can get it down to a quadratic, and then I can see if I can factor that quadratic, or maybe that quadratic's prime. I don't know yet, but that's my best bet. So what I want to do is I want to do my P and my Q. I want to figure out what all the factors of my constant are, and I want to figure out what all the factors of my leading coefficient are. So for my constant, let's see, it would be plus or minus 1. Let's see, 2, 3 doesn't, 4 doesn't, 5 does, and 10 does. So positive and negative versions of all of those are the factors of 10. Q is equal to 1, which makes it super easy, because it's just going to be 1. So that means that if I take P's and divide them by all of the Q's, I'm going to get 1 divided by 1, which is just 1, 2 divided by 1, 5 divided by 1, and 10 divided by 1. So this gives me 8 possibilities. Remember, it's positive or negative. So positive 2, negative 2, positive 5, negative 5, positive 10, negative 10. These are my 8 possible rational roots. You got to start somewhere, folks. So we're just going to have to start doing synthetic division and see if we can figure out which ones of these work. So we've got 1, 2, negative 13, and 10. Might as well start with 1. So if we start with 1, 1 times 1 is 1, 2, 2, negative 11. Nope, that one doesn't work. Don't waste a lot of time, folks. If one doesn't work, you just move on to the next one. So now I'm going to do negative 1. So 1, negative 1, 1, negative 1, negative 14. Nope, that's going to give me a remainder too. All right, 1, 2, negative 13, 10. Let's try 2. 1, 2, 4, 8. That would be negative 5, and that would be negative 10, and that would be 0. Bingo! So 2 actually ended up being one of the rational roots. So that means that x minus 2 is a factor, and I now have the other factor, x squared plus 4x minus 5. And so this is a quadratic. We know how to factor quadratics. If they're not prime, we have lots of tricks for factoring quadratics. Two numbers that multiply to equal negative 5 and add to equal positive 4 would be positive 5 and negative 1. And I have now factored that polynomial. And if I can get a polynomial in factored form, I can solve it. And so now I can actually answer the question and say, okay, so x must be equal to 2, negative 5, and it did say that 1 worked. So what did I do wrong over here? 1, 1, oh, this was 3. Okay, 3 times 1 is 3, and that would be negative 10. Oh, so that one did work. Wish I had caught that earlier. So that gives us all of the solutions for this one. We were able to factor it. We just had to find one of the rational roots so that we could divide it out and factor whatever was left over. So let's try one more. All right, so again, looking at this one, if I take out x squared, I get 3x minus 5, and if I take out 4, I get x plus 1. That's not a common factor, so factoring by grouping is not going to work for this one. Guys, always check. It is so much easier to just factor it if one of our factoring tricks works for it. So if it's a sum or difference of cubes or a difference of squares or quadratic type, always check before you start jumping in to try and find your rational root. So now I want to find my P and my Q. So P, let's see, factors of 4. 1, 2, and 4. And then factors of 3 would be 1 and 3. So now if I want to find my list of possibles, so my possible rational roots, divide all of those by 1. So I'm going to get 1, 2, and 4. And then I have to divide all of those by 3. So I could get 1/3, 2/3, or 4/3. So that gives us 1, 2, 3, 4, 5, 6, positive and negative. So we do have 12 possibilities here. Yes, that feels like it's a long list, but it's still easier to test 12 numbers than it is to just go through and try every random fraction. Like there's an infinite number of numbers in the universe. Narrowing it down to 12 has done a big service to us. So now we need to find the actual zeros. So we've got 3, negative 5, negative 4, and 4. So might as well start with 1. I've got 3, negative 2, negative 2, negative 6. Yep, that one's not a factor. So let's try negative 1. So that'll be negative 3, negative 8, 8, 4, negative 4, 0. Hey, that one worked. So negative 1 was a root. And since negative 1 was a root, that means x plus 1 is a factor. And 3x squared minus 8x plus 4 is the other factor. So now it's a quadratic. I need to remember my rules for factoring a quadratic. So 3 times 4 is 12. Two numbers that multiply to give us 12 and add to give us negative 8 would be negative 6 and negative 2. So x minus 6, x minus 2, but divide by 3 means that this is going to be x minus 2, and this is going to be 3x minus 2. So this factors to be x plus 1, x minus 2, and 3x minus 2, which means that if I'm solving, x is going to be equal to negative 1, x is going to be equal to positive 2, and x is going to be equal to positive 2/3. And so again, those numbers are all on my list of possibles. But once we find one that works and we've divided it out, we can then try to factor whatever is left over. Sometimes that might be a cubic power. Maybe factoring by grouping works, but if it doesn't, we can keep going down the list and find another one. It's just we're going to divide this polynomial instead of dividing the whole large polynomial. We just want to keep dividing out factors till we get to a point where we have all of the factors, or it's down to a quadratic and we can just factor it on our own. But that is how we find those factors when it's not one of our factoring tricks that will work on the polynomial.